Hello, welcome everyone. I'm Jing from Tsinghua University. Here I'm going to introduce our recent research on browser API fuzzing. There are lots of works on fuzzing individual submodules of browsers, like fuzzing JavaScript engines. But today, we focus on the whole browser fuzzing. It goes through a decade of research and starting from 2011, fuzzing the whole browser is a popular way to find bugs in rendering engine. And browser fuzzers become more and more powerful. Their generation strategy is not only syntax aware, but also context aware and semantics aware. Their common goal is to generate HTML files that explore browser states, and if we are lucky enough, the fuzzers will trigger some memory corruptions. So, how do the browser state change? The key to manipulate browser state is browser API. The APIs are exported by browsers through their JavaScript engine, and they can control browser state transitions. The backend logic of browsers is very complicated. For example, if we call the append child for element, its backend logic will update the rendering tree and recalculate the layouts and geographies of all elements. And if we set the style of an element, it will append the multiple relevant elements. If we set the height of an element, it will recalculate the layouts again for all elements. And browsers usually use some black magic for performance consideration, so it's very difficult to be bug-free. As fuzzer developers, we may wonder how to explore deep states of browsers, and obviously, we should make these API invocations highly depend on each other, so that their interaction logic can be covered. So, how do we determine the dependency relation between two APIs? Considering these two APIs, it seems that they have a relation with each other because they belong to the same element object and accept identical input types. But if we dig into their backend logic, we will find that they do not access any common memory locations. So they actually, in memory level, they do not interfere with each other. So why is the memory relation important? Why should we know the memory relation between APIs? Because putting two memory irrelevant APIs into a test case will not trigger any interesting behaviors. For fuzzing effectiveness, we would like to see that each generated input contains more highly dependent API invocations. Here we present a motivating example. There is a test case containing a lot of API invocations. Let's focus on this statement. It sets the current scale of a SVG element. And the two previous statements, document.write and body.appendChild, seem nothing to do with the statement of the setting current scale in the API type level. But their backend logic will commonly visit some memory locations. Let's focus on the backend logic. The setter of the current scale API does visit the memory locations modified by the previous two APIs. In another word, its logic will be affected by them. Such a memory modify and reference relation is implicitly present in API combinations, and we should find it out to facilitate our fuzzer's input generation. So, motivated by the example, in the paper we present, we propose Minerva, a new browser fuzzer, trying to see through model-ref relations between APIs and use the relations to guide its input generation. It consists of a two-stage design. First, during preparation, it analyzes the model-ref relations through dynamic traces. It first collects API specifications and use a custom instrumented browser to execute some workload inputs to collect traces. And finally, by analyzing these traces, we can know the model-ref relations between APIs. Next, during fuzzing, every time we want to synthesize an API invocation, we should consider the collective model-ref relations. We design a weighted API selection module. In this module, we prior the APIs that is more related to the previous generated API invocations. And after that, we synthesize a semantic-aware invocation for this API. By this way, we can generate a high-quality test case for fuzzing. Now we talk about some details about the two stages. And the first is the dynamic model-ref analysis. Basically, our approach is to use a custom instrumented browser to execute some workload inputs. So we can have some traces which record the way that APIs store or load memory locations. And based on that, we can build the model-ref relations. And this approach is unlikely to over-approximate relations because every built relation has a concrete proof thanks to the dynamic analysis. And we also try to reduce the runtime overhead by only focusing on the memory locations commonly visited by multiple APIs. So, for example, the access operation on local variables will be ignored. And to achieve this goal, we perform a data flow analysis on the browser source code to see which memory locations is worth to record. Next, we talk about the guided input generation. Every time we want to synthesize an API invocation, we consider the collective model-ref relation, and we perform weighted selection for those API candidates. And in addition to the relation guided, it is also context-aware and semantics-aware. Because of the collective API specifications, we can make every synthesized invocation semantically correct. And next, we thoroughly evaluate Minerva. For this part, first, we conduct 24-hour experiments, and each is repeated for 5 times. And we compare our approaches to existing state-of-the-art fuzzers. And the target browser for fuzzing are WebKit, Firefox, and Chromium. And the result shows that Minerva can achieve more coverage and generate more compact test cases and trigger more unique bugs compared to the existing fuzzers. Next, we conduct experiments to see if the model-ref relations truly contribute to making test cases less redundancy. And the answer is yes, the relations are helpful. As receiving more relations, Minerva will generate more compact test cases. And of course, we also apply our approach to discover new bugs. And there are 35 new bugs are discovered by Minerva. 26 have been confirmed, out of which 20 have been fixed, and 5 have been assigned new CVEs because of their security consequences. To sum up, we propose Minerva, a browser fuzzer, and its goal is to generate dependent API invocations, and its method is to generate test cases guided by model-ref relations. And it is open source at this repository, and welcome to use it. And please leave a star if it is helpful. And that's all. Thanks.